Good morning once more. I am Azinwie Zama Ambe. I'm talking to you from Ljubljana. I will be presenting my thesis at the BIM A+ International Conference on the topic, a study of practical BIM interoperability for implementation of workflows for structural modeling, analysis, and design. This work was carried out in the University of Ljubljana under the supervision of Professor Tomo and my co-supervisor, Professor Primoz Moze. We'll go straight to the presentation. As introduction and the problem statement, the construction IT industry has been undergoing some transformation over some decades now, over a decade and plus. And the literature review of this work has been covered already, showing the theoretical relationship between BIM and structural engineering. And so the goal of this work is actually to develop a workflow for implementation to enhance BIM practices among structural engineers, architects, and designers. And also the research focuses on interoperability, collaboration among structural BIM applications in conjunction with collaborative delivery and structural BIM projects by interdisciplinary teams. So the problem we have today in the structural design office is we have lack of collaboration between structural engineers and design architects. There is no implementation of BIM practices in reality in the structural design offices. And also we have the lack of BIM workflow in conjunction with the available softwares in each design offices. This diagram we see here actually represents the current state of the construction IT industry. Some years ago, how communication used to be made between the different interdisciplinary teams. We see that we have an ad hoc communication that doesn't flow between each team. And so with evolution, we have come to realize that with the help of BIM, we have a standardized central platform for building information exchange and which ameliorate communication and cooperation between design teams. So how is this done? This can be done through the help of IFC and also direct links that will be seen subsequently. The methodology of collaboration that we'll be implementing here will actually be discussed from this workflow. From here, we can observe that we have the architectural collaboration workflow from a BIM authoring tool that is from sharing information from an architectural model between an architectural model and structural analysis tool. So at the beginning, we see the workflow of an architect when a project is being initiated, how the architect initiates the project between its own team, and how information is being exchanged between other teams. We see the workflow of the structural engineering team and how collaborative they are within themselves, and also how information is being exchanged between them. And also there's actually a method of communication that permits that they could exchange information between themselves. And information have been exchanged through message flows. We have sequences, information relationship. We have material information that have been exchanged at each step based on the type of project and the goals to achieve on milestones. We have material parameters. We have geometrical information as well that have been exchanged at the early stage of the design. Our main focus of this work is actually characterized on this little diagram we see here. What I'm trying to establish here is to migrate from a BIM authoring software used by an architect, say Autodesk Revit, into a finite element method of finite element analysis software, where we have to transfer a model with load combination load cases into a finite element platform without remodeling, and which can automatically be updated without remodeling. So we can actually see a definition of interoperability. What is interoperability? Interoperability is actually from the structural analysis point of view. It is the ability to exploit information or data from one platform to another. And if we receive an information or a model from an architect, like this 3D model, how can we work in collaboration with the architectural team in a complex structure while keeping track of all the updates that have been made on the structure or on the design phases? And so we have different types of communication, as I earlier mentioned, and we will be elaborating a lot more on the cat links and the direct links rather, because the IFC has been covered. We have actually seen presentations that have been presented with the IFC, the type of data exchange. And since we are dealing with finite element method data transfer, we are going to focus more on the direct links that collaborates more with this BIM authoring Autodesk software. And so I will go directly into the workflow and the communication, how the workflow between Autodesk Revit and CI Engineer works. Why do we choose here? Excuse me, we choose those two basic structural final element softwares because these are the softwares that are available in the Slovenian and the Scandinavian market. In most of their design offices, these are the softwares that have been applied, that have been used. And CI Engineer is an excellent software when it comes to engineering report organization, or generating quality engineering report. We have CI Engineer for that. And we will be using Tekla Structural Designer, which is an advanced BIM structural design software as well that is being implemented when it comes to steel structures. And so when we have to implement the workflow between Revit and CI Engineer, we begin by creating a structural model in Revit, meaning we can collaborate, we can work together with the architectural model, we can define our grids, basic grids and basic structural elements like the columns, and we take it from there. We start by creating the structural model in Revit, we create the analytical model in Revit, and we export it to CI Engineer using the Tekla, the CI Engineer direct link, the cat link rather. We do the analysis in CI Engineer, we do the designing in CI Engineer, and we export back to Revit for possible update in case the sizing of the structural elements have changed. And this is actually an application of the workflow between Revit and CI Engineer. We have this hall that was modeled in Revit structure, and we have to actually convert this structural model into an analytical model so it could have all the properties of load combinations and all the load cases and the load combination. And this is being done by the help of this cat link. The cat link is a bi-directional link, meaning it works on both directions. We can actually do an update in Revit, and we get the same update in CI Engineer, as well as changing something from CI Engineer and getting the update back into Revit. This is actually the result of what we have in the CI Engineer workspace after doing the direct mapping into this workspace. Actually, there will probably be problems, and those are the problems we are trying to solve within this workflow. When we do a mapping into this structural engineering, we will actually have some difficulties, we'll have some challenges with the mapping of the materials. Like if you see my screen, you will see we have some few materials that were not properly mapped into the CI Engineer workspace due to some like we have 22 elements that were not properly mapped these 22 elements are the footings that were designed into Revit structure, which were not recognized by this structural finite element structural tool. So what do we do when we have a complex structure? We have to make sure that the structural elements we are mapping into these softwares are actually identified to be structural elements. They can be read and understood by this finite element rule. And so the classification of each element while modeling is very important. And we also have to define the design codes and appropriate materials used on them. So without wasting time, we'll also look at the workflow between a CI engineer and Tekla structure, meaning after doing the structural analysis of a structure, we can actually share our data back to the architect through the direct link that maps the information back into Revit, or also we can share our information into Tekla structure for designers to do the steel detailing for shop drawings and other related disciplines. So the interoperability workflow from modeling and analyzing in the SIA workflow into, in the SIA platform into Tekla structural platform is actually being done like this. We start by creating our model into Tekla, like we have this simple model that we model into CI engineer. We do the loading cases, we do all the designing, we size all the structural element, and we use the link. We use the CI engineer direct link to map this structure back into Tekla structure, and this is the result we have. Here you will see that we have a perfectly mapped model into Tekla structure without any loss of information. This is because the design codes were well defined. The structural elements were well mapped, and we didn't experience any loss of information in this case. In the same way, we did the same back into Revit, and we didn't have any loss of information, meaning this workflow actually works perfectly. And so the main objective of this work is actually to define a workflow that can be implemented in a design office. So many design offices face a lot of challenges in implementing BIM because first, they don't have trained people in their team that could actually implement BIM workflows. There is no defined workflow between the architect and the designers and engineers, as I earlier mentioned. And so this is something that we brought up to propose and test with the available software that some of these design offices use here in Slovenia. So we actually begin with this. This is actually let me call it the milestone of this workflow, meaning we can actually we are trying to implement a workflow using Trimble Tekla Trimble softwares, meaning we start the design from Tekla Structural Designer. We get information, we collect all the information from the architect, from Autodesk Revit, maybe using the DXF, the DGN or DWG or IFC file, and we can actually map it, or we export it into Tekla Structural Designer to define the grid lines for the preliminaries. And we start by defining the structural elements, that is positioning the columns, the beams, and all the rest, the slabs. We do the designing, and we can actually size the secondary structural element for traffic items. Those are the bracing case. If I'm working with steel structures, we could actually size the bracing element, and we can also design the connections, and we can check clash detections to see if everything is in place. We could go for rebar designs, we could go for construction documentation, and we can actually do the detailing and the shop drawings, all using Trimble Tekla softwares. But also when we have external softwares, we can also collaborate with them. As we see the integrated design and collaboration workflow, meaning if we have after designing, after calculating the structure and having all the forces, getting all the appropriate elements well sized, we could decide to share the model with an external software, either CI engineer, or we could actually take the case of connections. We could actually use the BIM link to share the model to design all the connections using IG Statica, which is appropriate for steel connections. We could also share the model using Trimble Connect for better collaboration. We could also share the model using Tekla structure for the entire steel detailing. And we could use the Tekla power fabrication to define the sequences of manufacturing the shop drawings in general. And so after implementing or after proposing this workflow, we had to implement it on the case study to see how it works and how we can help the design office. And so we have a case study here. It's actually a simple case study of a hall that was designed using the European norms, the Euro code, with French national annexes. Why do we use French and national annex? We use French national annex because this project is actually a real project and had some properties that were given to implement for the project. It is actually a warehouse that is having a height up to the roof level of 5.626 meters. The X directions, at the X directions, we have four bays of 5 meters, that 4 spacings of the structural grid at 5 meters, and on the Y direction we have actually a total length, the wide of 10 meters. The self-weight of the frame is automatically applied, and also the dead load is considered to be 0.6 kilonewton per meter square. We had the roof imposed load as the snow load at 1 kilonewton, and the wind load was automatically generated by the wind wizard in the Tekla structural designer, as we see below. And so after sizing this, designing this structure using Tekla structural designer, we took into consideration the embodied carbon design of the structure, which Tekla structural designer is an excellent software that gives a good result for that, to actually keep the structure green, eliminating all the carbon content in the structural documentation and up to the execution phase. So we have to share the model to the architect with a drawing back to the using the integrator for Tekla for structural designer. And this is actually what we had after doing the exportation into Tekla structure. You see, we have the basic structural element that were sized and were mapped back into Revit. We have also the Tekla structural export that we had this element into Tekla. We observed that we had some missing elements into the while exporting to Tekla structure, because the bracing elements were absent, the polines, the main polines were absent, the columns and the rafters were present, which are the principal structural elements that we really need. The grid lines were maintained at their initial positions, and these are the basic information that we need to kick off with the project. And after choosing the appropriate software to do the designing, that is for the shop drawings and generating the appropriate general arrangement drawings, we had to come out with this. We maintain the positions of the main structural elements as a column, the rafters. We incorporated the polines, the bracing elements, as you can see, and we did the connections. We calculated all the connections using Tekla, using IG Statica. and auto map it into the Tekla model, which is auto adjustable.
I'm sorry to interrupt you. You are presenting a very detailed work. I just ask you to be more synthetic because you have exceeded the time for presenting.
Okay.
So yeah, thank you.
Okay, I just have one slide to complete.
Okay, thank you.
Yeah,
thank you.
and this is actually what we have after doing the design of all the structural elements, sizing, mapping, and generating all the construction drawing, doing the preparation for the fabrication, and we had to come out with an extract of this as a presentation, and we had the elements that were automated and updated into the Revit model and shared with the architect to modify the architectural plans. And actually, this is the end of my presentation. Thank you for your time. And if you have questions, please kindly ask.